The abyssal frontier, geological force, and the pioneers welcome back to Ghost Vibes. Today, we confront the most alien and least explored domain on our own planet, the Mariana Trench. This immense oceanic chasm, located in the western Pacific Ocean, is a seismic scar, a terrifying reminder of the raw, violent power contained within the Earth's tectonic plates. It is the deepest part of the global ocean, plunging down to nearly 11,000 meters, 36,000 feet. The specific pit known as the Challenger Deep is the ultimate geographical frontier. Its depth is so profound that if Mount Everest were placed within it, its summit would still be submerged by over 2 kilometers of crushing dark water. This extreme geography is the direct result of subduction, a continuous geological process where the vast Pacific Plate is being forcefully driven beneath the smaller Mariana Plate. This slow-motion planetary collision creates the extreme, crushing depth and the powerful seismic instability that defines the entire region, making it a critical zone for understanding global tectonics and crustal recycling. The physical parameters of this environment impose absolute limits on exploration and survival. The immense hydrostatic pressure is the primary hostile force. It exceeds 1,000 times the atmospheric pressure felt at sea level. To survive here, any structure, whether biological or engineered, must withstand forces that would instantly flatten an unprotected object and severely compress even the hardest steels. This factor, combined with the perpetual absolute darkness, where no sunlight penetrates, and the near-freezing temperatures, hovering just above Dodeksang, creates an environment of profound physical difficulty. The trench is a natural anti-laboratory, a place where standard human engineering and biology break down entirely. Yet, it is precisely these extremes that make it scientifically invaluable, serving as a unique observatory for deep Earth processes, the astonishing resilience of life, and the strange physics of materials under colossal stress. Due to the overwhelming difficulty of sustaining activity there, the global scientific community often acknowledges the Challenger Deep as a greater technological and logistical challenge than the exploration of the surface of the Moon. The exploration history of the trench is remarkably brief, defined by technological battles against overwhelming odds. The first reliable depth measurement was achieved in 1951 by the British survey vessel HMS Challenger II, which lent its name to the deepest point. The true pioneering human effort came in 1960 with the dive of the bathyscaphe Trieste, a U.S. Navy vessel piloted by Swiss oceanographer Jacques Picard and U.S. Navy Lieutenant Don Walsh. The Trieste's mission was a high-risk endeavor, relying on extremely thick steel and an ingenious ballast system. The entire journey into the abyssal black took 5 grueling hours. Upon reaching the bottom, they spent a tense, brief 20 minutes observing the seafloor. Their subsequent report mentioned seeing what appeared to be a flatfish, a sighting that, if true, suggested complex mobile life could thrive at that depth, though the observation remains scientifically debated. The success of the Trieste demonstrated that the abyss could be reached, but the technology was so specialized that it led to a half-century gap in manned visits. The second manned descent, a massive leap in technology, was conducted in 2012 by filmmaker and solo explorer James Cameron aboard the custom-built submersible, the Deep Sea Challenger. Cameron's mission aimed to blend deep-sea science with cinematic documentation, utilizing advanced composite materials to endure the extreme pressures. Despite the technological progress, the dive was a constant battle against the elements. The pressure caused structural failures, including a major hydraulic system leak that threatened crucial sample collection arms, and the sub's components showed dangerous warping. Cameron's successful return yielded invaluable high-resolution footage and geological samples, vividly documenting the unsettling, desolate, mud-covered plain of the Challenger Deep. This mission reignited public interest but also highlighted the immense logistical and financial burden. Only 3 individuals in human history have ever reached this deepest point, a number that starkly contrasts with the 12 people who have walked on the Moon. This minimal visitation history proves that the Mariana Trench remains the ultimate technological gatekeeper, fiercely guarding the secrets sealed within the Earth's deepest fracture. Our quest here is driven by the realization that to fully understand the Earth, we must first confront and conquer its most overwhelming challenge: the unseen life, dark ecology, and the chemical blueprint. The crushing physics of the Challenger Deep is only one side of the enigma. The other is the astonishing life that not only survives but thrives in this extreme environment. The trench presents a biological paradox that fundamentally changed our perception of where life can exist on Earth and potentially elsewhere in the cosmos. When scientists finally managed to collect samples from the abyssal plain, they discovered that the bottom was not a sterile, dead void, but a complex, though sparsely populated ecosystem. This unique ecology operates under biological rules that are almost entirely foreign to our surface world, offering a chilling glimpse into the absolute limits of biological resilience. This deep ecology is primarily defined by the principle of chemosynthesis, a monumental departure from the sun-dependent photosynthesis that fuels virtually all life above the trench's dark ceiling. In the aphotic zone, sunlight is irrelevant. Instead, these deep-sea ecosystems rely entirely on the Earth itself for energy. Hydrothermal vents and cold seeps on the seafloor act as chemical generators, spewing superheated mineral-rich fluids, loaded with compounds like hydrogen sulfide, methane, and various metal sulfides that originate from the planet's crust. Within this toxic high-pressure plume, specialized chemoautotrophic bacteria harness the energy from these chemical compounds to produce organic material. These bacteria form the absolute foundational base of the food chain, sustaining all subsequent life in the trench. This profound discovery proved that life can be initiated and sustained in environments entirely divorced from solar energy, a finding with monumental implications for astrobiology and the search for life beneath the icy crusts of distant moons like Europa or Enceladus. The trench is essentially our planetary test lab for extreme survival, illustrating that energy, not light, is the true ultimate requirement for biological genesis. The most famous organisms adapted to this zone are the Hadal species, named after Hades, the Greek god of the underworld. These include the famously translucent Mariana snailfish, Pseudoliparis sueri, various types of scavenging amphipods, and unique bottom-dwelling sea cucumbers. These organisms possess incredible biological adaptations to resist the crushing forces. The extreme pressure would instantly destabilize the cellular structures and denature the proteins of most surface creatures. However, Hadal species have evolved high concentrations of organic molecules, most famously trimethylamine N oxide, TMAO. TMAO acts as a potent counter-pressure agent, chemically preventing the water molecules from compressing and destroying the vital proteins and enzymes inside their cells. Lacking gas-filled swim bladders and heavy bone structures, their bodies are often soft, gelatinous, and highly flexible, maximizing their resilience in the dense water column. They are slow-moving shadows, perfectly tuned to the energy-scarce environment, where every calorie consumed is essential for survival, often involving long periods between feeding events. The trench, however, is not a perfectly closed biological system. A constant silent deluge of organic matter, known as marine snow, drifts down from the sunlit upper layers. This snow, composed of dead organisms, microscopic particles, and detritus, can take weeks or months to reach the abyssal floor, but it provides a critical secondary food source. This sinking material sustains large populations of amphipods, small, voracious scavenging crustaceans that are crucial for recycling nutrients. It is the study of these scavengers that provided one of the most disturbing links between the surface and the deep. The retrieval of amphipods from the Challenger Deep revealed alarmingly high concentrations of microplastics and persistent organic pollutants, POPs, in their digestive systems. This single finding shattered the philosophical notion of the Hadal zone as a pristine, untouched wilderness. It confirmed that even the deepest, most isolated parts of our planet are effectively the final collection zone for human contamination, making the trench a profound geological scale mirror reflecting the negative ecological reach of our civilization across the globe. The trench's existence is a critical probe into the nature of existence itself, providing data that helps us understand the fundamental requirements for biological life and the terrifying limits of human impact. The Titanic submersibles and the technological race. The intense scientific value of the Mariana Trench has driven a relentless, high-stakes technological race, transforming deep-sea exploration from simple scientific endeavor into an engineering war against physics. The handful of manned descents are mere footnotes compared to the ongoing, largely unmanned effort to map, sample, and understand this abyssal frontier. The key challenge remains the design and deployment of specialized submersibles and landers that can withstand the colossal pressure, a challenge that has claimed countless pieces of equipment and billions of dollars in investment. The development of these deep-sea vehicles is itself a dark mystery, pushing the boundaries of material science to their absolute breaking point. The vast majority of modern exploration relies on autonomous underwater vehicles, AUVs, and remotely operated vehicles, ROVs. AUVs are self-propelled robots that can navigate and collect data autonomously, often mapping the seafloor with high-resolution sonar. ROVs, on the other hand, are tethered to a surface vessel, allowing real-time control and direct data transfer. These vehicles must be built with revolutionary materials. Typical steel or titanium hulls often prove insufficient. Engineers resort to specialized ceramics, reinforced acrylics, and complex layered alloys that distribute the hydrostatic pressure evenly. Failure of even a microscopic weld or a tiny flaw in the material structure results in instantaneous catastrophic implosion. The sound of such an implosion, when captured by deep-sea hydrophones, is described as one of the most chilling sounds in the natural world. A single, final, thunderous crack followed by an absolute terminal silence. The most critical and challenging instruments are the landers, stationary platforms that are deployed for long-term data collection. These landers are designed to free fall to the abyssal plane, where they activate collection mechanisms, bait traps for hadal species, and monitor seismic and chemical activity. Their construction is often a masterclass in minimalist resilience. The pressure chambers that protect the electronics and scientific equipment are usually made of thick, high-strength titanium or highly robust ceramic spheres. After completing their mission, the landers drop heavy ballast weights and use buoyancy materials to ascend back to the surface. However, a significant percentage of these landers are lost forever due to corrosion, mechanical failure under pressure, or the simple failure of the release mechanism, swallowed by the abyss, becoming permanent, unrecoverable technological ghosts in the Challenger Deep. The technological race has recently focused on creating more sustainable, continuous access. Japan's Kaiko and China's Fenduji submersibles represent the pinnacle of current capabilities. The Chinese manned submersible Fenduji, Striver, has completed multiple successful manned descents to the Challenger Deep, breaking the monopoly previously held by the US and independent explorers. Its success relies on an extremely advanced, domestically produced titanium alloy hull, a technological achievement that underscores the geopolitical significance of deep-sea exploration. Nations are not merely searching for knowledge. They are vying for access to potential deep-sea mineral resources, including cobalt crusts and rare earth elements, which are abundant in the Pacific seabed. The control of these deep-sea territories and the technology to reach them is rapidly becoming the next great arena for global competition, turning the scientific quest into an industrial and military concern. However, the rapid push for technological supremacy often overlooks the ethical and ecological questions. The very act of deep-sea sampling, particularly the use of large nets and aggressive baiting, disrupts these fragile, slow-growing ecosystems. Scientists are battling to implement strict international protocols to protect these unique biospheres before the technological rush for minerals permanently destroys the biological and geological record preserved in the trench. The deepest dive is thus a complex philosophical confrontation. Is humanity willing to risk the destruction of the oldest, most resilient life on Earth for the sake of resources and geopolitical gain? The silence of the abyss is a constant, terrifying question mark hanging over the ethics of our final frontier. The sound of silence and the deepest pollution. The Mariana Trench, despite its profound remoteness and isolation, is anything but quiet. The deep ocean is a world saturated with sound, but the specific acoustic environment of the trench holds some of the most unsettling and mysterious auditory phenomena on the planet. The study of this acoustic environment is crucial because sound travels 5 times faster in water than in air, making underwater acoustics the primary way researchers gain a sense of the geological and biological activity in the perpetual darkness. However, the sounds recorded often pose more questions than answers, giving rise to persistent maritime mysteries. The geological sounds of the trench are often the most intense. The constant slow-motion subduction of the Pacific Plate beneath the Mariana Plate generates immense friction, leading to frequent, though often low-magnitude, deep-sea seismic events. Hydrophones, specialized underwater microphones dropped into the abyssal zone, record the low-frequency groans and deep structural cracks of the Earth's crust as the plates grind against each other. More dramatically, the intermittent activity of the serpentinite mud volcanoes and hydrothermal vents creates a symphony of bubbles, pressurized releases, and mineral precipitation, which sound like strange, unnatural rumbling and hissing within the silent water column. These deep earth murmurs offer direct acoustic evidence of the geological forces that birthed the trench itself. However, the human element has tragically introduced the most pervasive and chilling new sounds. Despite being the most isolated place on Earth, the trench is not safe from arsenic pollution. Decades of naval sonar testing, shipping noise from surface vessels thousands of miles away, and the seismic surveys conducted by oil and gas exploration companies have saturated the global ocean with noise pollution. These low-frequency sounds travel immense distances and penetrate even the Challenger Deep. For the hadal species, which rely entirely on sound and vibration to navigate, hunt, and communicate in the perpetual darkness, this human-generated cacophony is a disruptive and potentially lethal intrusion. The constant acoustic interference may effectively deafen or disorient creatures that evolved in silence, disrupting a delicate, ancient biological balance. Even more disturbingly, the silent intrusion of microplastic pollution highlights the global connectivity of the ocean. When scientists analyzed the amphipods retrieved from the absolute bottom of the trench, they found that virtually every specimen contained synthetic plastic fibers and microparticles in its gut. This discovery confirms that the trench is not a pristine environment, but rather the ultimate global sink for human waste. These microplastics, originating from surface-level plastic debris that has degraded and sunk over time, travel down through the water column, becoming integrated into the deep-sea food chain. The hadal species are, in effect, consuming the remnants of our modern civilization. The biological implications of these pollutants, the long-term effects of ingesting plastics and the associated persistent organic pollutants, POPs, on the cellular integrity of these extremophiles are only just beginning to be understood. The silence of the abyss is, therefore, not just being broken by man-made sound, but it is being filled with man-made debris, turning this ultimate sanctuary into a silent tomb of our own making. The greatest secret of the Mariana Trench might be the depressing confirmation that there is nowhere left on Earth untouched by humanity. The forbidden zones and unconfirmed sightings. The Mariana Trench, by its very nature as a barely glimpsed frontier, is a breeding ground for unsettling speculation and stories of the unconfirmed. Given the profound limits of our exploration technology and the fact that 95% of the deep ocean remains unmapped, the question of what else might inhabit that perpetual darkness is a persistent source of both scientific curiosity and deep-seated fear. The sheer volume of the unexplored habitat means that the deep could easily conceal species of enormous size or radically different biology, creatures that only emerge when the lights of our submersibles are not present. One of the most persistent and compelling speculative mysteries surrounding the trench is the possibility of genuinely colossal, deep-dwelling megafauna. The most famous example is the enduring hypothesis that a surviving megalodon, the giant extinct prehistoric shark, could potentially inhabit the abyssal zone. While mainstream science largely dismisses this as fantasy, the sheer depth and thermal stability of the hadal zone offer a theoretical refuge. The ocean depths have historically provided sanctuary for other creatures thought long extinct, such as the coelacanth, a living fossil fish. The theory suggests that a highly adapted lineage of massive apex predators could survive on the steady, if sparse food supply of marine snow and large sinking carcasses, retreating to the safety of the extreme pressure zone to avoid modern-day competition. The occasional discovery of unusually large bite marks or broken equipment retrieved from deep moorings serves to fuel this compelling, albeit terrifying, hypothesis. Beyond biological speculation, the extreme geophysical anomalies of the trench have led to theories of forbidden zones and unusual human activity. The trench is a major site of subduction, and the pressures are so immense that they create unique geological formations. Unconfirmed reports from some early experimental robotic probes have alluded to highly reflective, metallic debris resting on the seafloor, far from known shipping lanes or military test sites. These ambiguous findings, combined with the geopolitical interest in the region, have occasionally given rise to conspiracy theories suggesting the trench is used as a covert dumping ground for military waste, lost experimental technology, or even highly sensitive, unrecoverable satellite debris. The almost instant implosion of any failed submersibles ensures that any such artifacts would be virtually impossible to retrieve or verify, leaving the truth shrouded in ambiguity and the deep's crushing silence. Furthermore, the isolation of the trench makes it a prime candidate for the discovery of truly unique microbial biospheres, life that evolved separately from all other terrestrial life. Scientists are particularly interested in the chemolithoautotrophs, microbes that derive energy from inorganic compounds in rocks. The deep rock fissures and hydrothermal vents may contain organisms that are structurally and genetically distinct, potentially representing a second genesis on Earth. This possibility raises a profound question. If we discover a form of life that is not related to the universal tree of life, Luca, what are the ethical implications of studying it, and how should we protect it from contamination by our own microbes? The trench is thus a silent, living archive of the planet's oldest, most resilient biological information, a history that is rapidly being contaminated before it can be fully read. The fear is not just what we might find, but what we might destroy through our intrusion into this most ancient of natural laboratories, the unending quest in the ethical abyss. The exploration of the Mariana Trench stands as humanity's most profound confrontation with a final terrestrial frontier. The trench is not merely a geological feature, it is a repository of planetary history, a crucible of extreme life, and a complex mirror reflecting both our technological prowess and our environmental failures. As the initial excitement of mere descent has passed, the focus has shifted to the difficult, long-term scientific and ethical questions that the trench forces us to confront. The ending of this story is not a discovery, but an unending quest defined by the balance between scientific curiosity and ecological responsibility. The geopolitical race for deep-sea dominance is perhaps the most immediate threat to the trench's integrity. Nations like China, Russia, and the United States are heavily investing in Hadal Zone technology, driven not just by scientific curiosity, but by the hunger for deep-sea mineral resources. The trench and its surrounding areas are rich in manganese nodules, cobalt crusts, and rare earth elements, minerals essential for modern electronics and green energy technology. The prospect of deep-sea mining looms large. If commercial deep-sea mining begins, the process of dredging the seafloor will create vast sediment plumes that could drift for hundreds of miles, suffocating the slow-growing, fragile chemosynthetic ecosystems. The recovery rate for these Hadal species, which reproduce and mature over vast timescales, is almost zero, meaning that the ecosystem, once destroyed, would likely be lost forever. Scientists are urgently advocating for the entire trench to be declared a permanent international marine protected area, arguing that its scientific and historical value far outweighs its temporary mineral wealth. Philosophically, the trench challenges us to define humanity's role in the universe. If the trench contains a second genesis of life, as some theories suggest, its destruction would mean the loss of unique biological information that could redefine our understanding of existence itself. The discovery of microplastics in its deepest dwellers serves as a sobering reminder that we cannot explore the cosmos responsibly if we cannot even protect the final frontier on our own planet. The trench has become a measuring stick for our environmental maturity. It tests our willingness to restrain our extractive impulses in favor of preservation and long-term scientific knowledge. The abyss demands a maturity we have rarely shown. Looking ahead, the next generation of exploration will move beyond simple submersibles to long-duration monitoring. Future missions plan to deploy Hadal observatories, permanent robotic stations anchored to the seafloor, continuously monitoring seismic activity, chemical fluxes, and biological movements for years at a time. This transition from fleeting visits to sustained presence will finally provide the continuous data necessary to truly understand the trench's role in the global carbon and tectonic cycles. However, even with the best technology, the ultimate mystery of the trench may remain forever unsolved. It is a world that resists human intrusion, a cold, dark testament to the planet's vast, unconquerable secrets. The enduring silence of the Challenger Deep is a profound question mark, and the sound of its exploration is the sound of humanity coming to terms with the limits of its knowledge.